So Brewster's angle, polarization by reflection. Where is my chalk? Here it is.
Professor,
Yes.
is this something that I was able to see a reflection on the light when it was 90 degrees, like when they were 90 and
Yeah.
90? How does that work? Like I was able to see my reflection on.
Yeah, there's always some reflection, but we're for the polarizer, we're just worried about what gets through.
Oh, okay.
Yeah, what gets through it. Yeah. So can I erase this? Because I want to use the board for the next topic. Brewster's angle, yeah. So consider material here N1 and N2. Again, air and water maybe. Take the perpendicular. Here is the angle of incidence. Here is the angle of reflection. Okay? And then there is the angle of refraction. There is a special angle, theta 1, okay? There is a special angle called Brewster's angle, is such that if you have the right theta 1, the reflected ray and the refracted ray will make 90 degrees. So if, let me write it, if the outgoing, if the reflected ray and refracted ray are perpendicular to each other, this means perpendicular to each other, we say theta 1 is equal to theta b, Brewster's angle. If they make 90 degrees with each other, this angle happens to be 90, then you got Brewster's angle. Okay? So let's use geometry to find it. So first of all, we know using Snell's law that n1 sine of theta 1 will equal to n2 sine of theta 2. You agree with that? Then we get n1 sine of, suppose now if theta 1 is equal to theta Brewster, if it's equal to theta Brewster's angle, then we got this. n1 sine of theta b is equal to n2 sine of theta 2. But look at the geometry of the product. What is theta 1 plus 90 plus theta 2? 180. Therefore, theta 1 plus theta 2 are 90, right? Theta 1 plus theta 2 is 90. Therefore, theta 2 will equal to 90 minus theta 1. Right? Theta 2 will equal to 90 minus theta 1. So here I'm going to replace this. Theta 2 will equal to 90 minus theta 1. And theta 1 is we're just calling it Brewster's angle, because that's when this happens. Okay? Now, use trigonometry. What is sine of 90 minus theta b? Cosine of theta Brewster, right? So if sine of 90 minus theta is the cosine of theta. So you get n1 sine theta b B will equal to N2 times the cosine of theta B. Divide both sides by cosine and then both sides by N1. Then sine over cosine is tangent. Theta B is equal to N2 over N1. Now for theta, let's do an example. If N1 is air, maybe 1, and N2 is water, so it's 1.33, right? So let's calculate this theta Brewster, theta B, equal to tangent inverse of N2, which is 1.33, over 1, which is N1. You want to do that? And tell me what the answer is in degrees, because I don't remember. How many?
53 degrees.
53 degrees, okay, 53 degrees, upward 50. I don't know the answer. All right, perfect. Now, so that's how you'd calculate theta Brewster. We're not going to do much with it. But why would anybody care about this Brewster's angle thing, where they make 90 degrees? It looks like a mathematical problem. Well, the reason it's a special angle, it turns out, it can be verified experimentally or theoretically, that at this special angle, if you have n polarized light, the reflected one will be polarized at this special angle. So you have n polarized, what's reflected will be polarized. Okay? And there is a special polarization direction. It's actually perpendicular to the plane. But we're not going to do much with it. So that's why I think it's a good exercise about refraction, really, how to use the equation, Snell's law. So this ends this chapter. And the next one we're going to talk about lenses, mirrors, and maybe optical instruments. If I'm too behind, I will not talk about them. Because I care about lenses and mirrors, and then there are combinations when you combine lenses together. You can get telescope, microscope. So I'm going to erase the board and then start our lenses and mirrors. Okay. All right, so this is the beginning of chapter 34, lenses, mirrors. They call it geometric optics. So geometric optics. And they have a lot of words that they define, and I think it's worth it that they do go through the definitions. The first, object. What's an object? What do we mean by an object? An object is anything that it emits light, or maybe light seems to be coming from it. So how do I see you? Because, well, there is light, it reflects from you, and then I get that light from you, and then I can see you. So you're an object, I can see you. I'm an object, you can see me, right? So everything we can see is an object, okay? It could be a point. Usually we just use an arrow for an object to simplify. We're not going to draw a whole person or something. We're not going to be too artistic. So it's just enough to do an arrow, and then if we get an image, then brings us to the word image. Images could be real or virtual. So let me give you an example of an object and then an image. So a plane mirror is a mirror that is just flat, looks like a plane. And this is the mirror. Okay, I just drew the side. This is the non-reflecting side, and this is the side from which the mirror will reflect. So you're usually standing here, and then you can look at yourself, right? This is where you're standing. This is the side where it's glued to the wall. So now, let's say I have an object here. That's my object. It's an arrow. The distance between the object and the mirror, the mirror or the lens, will be called S. This is the distance from the object to the mirror. It's called S. And then, so this is the tip of the arrow. This is the tip of the arrow. We usually just draw a couple of rays, 2, 3, until we're satisfied. Just 2 or 3 we do. So we'll draw the one that goes straight. Here's a ray that goes straight. How would it reflect? It will get to the mirror, it will reflect. And it will reflect back on itself, right? Yeah. So this way, if it's just horizontal, the mirror is flat, it just makes 0 degrees with the normal, it just reflects back to itself, on itself. Let's draw another one. Maybe blue and red. Another one that goes like this. It will reflect, and the angle of incidence is equal to the angle of reflection. I'm trying to be as perfect as I can, but I probably will not do the best job. Okay. So that's another one. Let me draw a third ray, and that's it. Okay, the third one. Here's the third ray. Okay, here's the third ray. This is the normal, and so the ray will kind of go like this, right? This is the reflected. Now, if you're looking at the reflected rays, one of them is going like that, like going up, the other one is coming towards you, and the other one is going like this, downward, right? Our brain fills in the gap. Says, oh, they seem to be coming from something somewhere here. Right? The rays are going like this, so they must be originating from somewhere there. So where is that somewhere there? Let's draw the extensions of the rays. Because here, they're not going to meet here. So this one here, we go like that. And then the yellow one, where's yellow? Yellow one will go like this. And then the red one will extend like so. Okay? And they seem to meet, I kind of messed it up, but they seem to meet somewhere here. If I do it perfectly, you will have something like that. They seem to originate from somewhere here. Okay? And that's the image. This is the object. This is the image. The distance this way for the image, we call it S prime. Okay, S prime. So we need the sign convention. S prime, the image distance. S prime. By the way, some books use DI for the DO for the object, and then DI for the image distance. Some use S and S prime. I've seen U and V. U for the object, V for the image. So we'll just use what the book does. Okay, S and S prime. Although I'm not used to these. I'm used to DI and DO. Anyways, so S prime. It will be positive if the image is on the same side as the reflected rays. Positive if the image is on the same side as the outgoing rays, or reflected as the reflected rays. And then it's negative if it's on the opposite side as the reflected rays. In this case, where are the reflected rays? They're to the left of the mirror, right? Yeah. And where is the image? It's to the right of the mirror. So is it positive or negative in this case? Negative. So if, well, I would say, I don't want to write the whole sentence, I would just say negative otherwise, right? If it's not positive, it's negative. Okay, that's it. So that's the image distance. There is another one. We'll deal with what's called real images and virtual images. A real image is where the rays meet to form the image. A virtual image is where the extension of the rays meet, or the extensions of the rays meet to form the image. So in this case, is it real or virtual? It's virtual. This is a virtual. And then we also describe it by saying whether it's upright or inverted. In this case, it will be upright. The tip is up, so our image will form somewhere here, and then it will be upright. This is a plain mirror, so nothing special. Okay. Then we can use the angles, and we can show that S is equal to S prime. This distance from here to here, this magnitude, is equal to this magnitude. Okay. Let's see. How can I? What else can I say? Do you know how to show that they're the same magnitude? It's just by the angles, right? For example, if I this angle here is equal to this angle, right? Because this is a parallel. So if this is theta, then this is theta. If this is theta, then this also has to be theta. Why? Because this is a parallel, and this is parallel. So these two angles are corresponding, right? Or actually, no, they're not corresponding. This one and this one are corresponding, but this is the angle of reflection. This is the angle of incidence. This is the angle of reflection. So this has to be theta. So this one is also theta. Okay. This is theta. Yes. And then we know the tangent of theta from on this side, it's this over this is the tangent of theta, and this over this is the tangent of theta. But this is common to both, therefore this distance must equal to that distance. So for a plane mirror, for a flat mirror, the two distances are just equal to each other. Okay. So next, I want to talk about spherical mirrors. That's my next one. This one is just not much interesting stuff. Okay. Then you seem to have a question. Yeah.
Is it, actually, never mind, I'll be quiet.
I'm listening. The sign convention, there is one more sign rule, and I will talk about it, that has to do with spherical mirrors. Okay, with spherical mirrors. So plane mirrors, they're just flat, and what happens is you get an object, the image of the object will just be behind the mirror. Obviously, there's nothing behind the mirror, right? But the image seems to be behind the mirror. How far? Just the geometry would say it's the same distance. You get closer to the mirror, the image gets closer, right? All right. Yeah.
If you're wearing glasses, would that count as like a?
Glasses are lenses. Yeah. So we'll talk about glasses when we do lenses.
Like that would affect where you see the image, right? Like S prime would be different.
The image that's formed in the mirror, in the plane mirror, no, it will not affect it.
Like if you're nearsighted, the image would
Yeah.
seem. I don't remember if it's closer or farther.
Yeah, what happens is, we'll talk about lenses. So if I am nearsighted, you're very far away from me. And so what my lenses they do is, yeah, they bring your image to my near point, and then I can see your image. We'll discuss that. But these are just mirrors. So they only are governed. Mirrors are governed by reflection. Refraction is when you get lenses. Lenses, light actually goes through the lens. For the mirror, it just reflects, right? From this. So let's go through spherical mirrors. There are two types. There is the concave. This is a concave mirror. Okay, meaning this is the reflecting side. This is the reflecting side. This one is just behind the mirror. Okay. And then there is convex. Convex looks like this. So you would stand here. This is the reflecting side for a convex mirror. I do have a concave and a convex mirror. I'll bring them out in a moment. Is that clear? Concave, convex? Okay. Why are they called spherical? Well, if you continue the pattern, you will get a sphere. Continue the pattern, you get a sphere. Okay. Now, when you, let's say an object is here. This is the center. Let's say I have an object somewhere here. Let's say here's an object. If you send light, let's say this way, it will reflect somehow, right? All the reflections will be this way. Yes? There is no light that will go through. So all the reflected rays are on the same side as the center. All reflected rays are on the same side as the center. So in this case, so if, let me write here, if the reflected rays or the outgoing rays, if the outgoing rays are on the same side as the center, then R is positive. The radius of curvature is positive. We just count it as positive. If the outgoing rays are on opposite side as the center, if the outgoing rays are on the opposite side of the center, then R is negative. R is negative. So, which is to say, for a concave mirror, the radius of curvature is what? Positive or negative? For concave? Positive. Convex? Negative. Because for convex, you have, let's say I have a ray here. If I send this ray this way, it will reflect back on itself. If I send the ray here, it will reflect this way. So all the outgoing rays will be this way, but the center is over there. Okay. Center is over there. Okay. The next thing, let me show you what a concave and convex mirrors are. So, yeah, so this is a concave, right? This is the reflecting side. If you continue, you get a sphere this way. And then the convex. This is convex. That's the reflecting side. Yeah, that's it. Let's see what interesting stuff happens. Hopefully this is not blocking the camera, so let me remove that. Let's go with the concave mirror. Let's focus on that first. We will do it next time. We'll do using angles to figure out the image distance with the object distance and so on. We'll find the relationship between them. But I'm going to first mention by the way, this middle thing that runs through the middle of the mirror is called the optical axis. Just firm. And this is the center. See, that's the center. So if you were to, this distance from here to here is the radius of curvature, right? That's r. So the mirrors, they would have a property, a certain property, and that property is that if I send parallel rays, if I send the ray that's parallel to the axis here, to this axis, so here's the ray, I'm going to send it parallel, okay? I'm going to send it parallel. And the question is, how is it going to reflect?
It goes straight.
What does straight mean?
It comes to the sender.
It will reflect on itself?
It comes back to the sender.
Like this?
No, through the point that's.
Oh, it reflects through this point.
Yeah.
Okay. Would you say so? Almost. Almost. Yeah. Here's the, let's think about it. Let me draw a perpendicular, let me draw a line from here to here. Here's a tangent. What do we know about this line? It would be perpendicular, right, to the tangent? It would be perpendicular to the tangent. So this is the normal. At that particular point, this is the normal. So this ray makes this angle with the normal, that's theta. So we know the angle of reflection has to be where? Has to be equal. So I must have another angle here just as equal. This is theta. And so the ray has to pass this way. It has to pass through this. Okay. So it has the property that any ray that comes in parallel will get through this point here. So if I send another one, parallel, you can draw the angle of incidence, angle of reflection, and you will find that it will also almost gets through here. Almost. I say almost because it's an approximation. Okay. So all parallel rays will pass through the focal point. Okay. I'm not sure if I pressed record actually. I did. Okay. Yeah. So all parallel rays, they pass through the focal point. Is that clear? Yes. Let me ask you a question. See if you understand. Let's say I send a ray through the focal point. So let's say I send a ray now through the focal point. Let me use blue. So it's a little different. So I'm going to send a ray through the focal point. Can you tell me how it would reflect?
It will go back.
Oh, parallel?
It should reflect parallel. Yeah. Because if you send it parallel, it should reflect this way. Because let's reverse the process. If I send it this way, then it must go this way. That's angle of incidence equal angle of reflection. So it must be that way. So if you send it through the focal point, it will reflect back on itself. Now, this distance from here to here, from, let me use yellow now. Okay, so this distance from here to here is called F. Okay, this is F, right? That's the focal point, F. Okay, and what is this distance? What's this distance? From here to here, what's this distance? That's R. That's the radius of curvature. From the center to the edge is R. Now, what's the relationship between R and F?
F is half of it.
F, it looks like half, right? Yeah, and it is almost half, basically. And so let's figure it out a little bit more. Again, we'll do it next time with the angles, which might be a little better. So here is C, that's the center, and here is F. let's say, again, let me send a ray that is parallel. Okay, it will pass through the focal point, right? We said it will pass through the focal point, and we said this. If this is theta, this would be theta. Let me ask you the following. What would this angle be?
Would be theta.
Huh?
That would be
Would it be theta?
2 theta.
It would be 2 theta, yeah. Because look, this line here and this line are parallel. So this angle with 2 theta, they're alternate interior, right? So we get 2 theta. It's twice theta. Yeah. How about this angle here? What's this angle? This one.
Theta.
That would be theta, because if this is theta, this is theta. Alternate interior. Yeah. That's theta. Alright, so let me ask you now the following. This arc length, we usually put S for arc length, but I'm not going to use the letter S because I already used it for the image, the object distance. I would just write arc length is equal to what? Arc length is R times theta. Yes, it's R times theta. R times theta. And arc length is also approximately, I'm going to pretend that this is also part of a bigger circle. Approximately, huh? So what would this arc length be in terms of F and 2 theta? F times this angle, which is 2 theta. So it'll be F times 2 theta. I put approximately equal because this is not quite a circle. We're assuming the angles are small enough that I can do that approximation. So that means these two must be equal. So R theta is approximately equal to F times 2 theta. So that means R would be twice F, which means F would be half of R. R over 2. So the radius of curvature would be twice the focal length. Okay? Radius of curvature is equal to twice the focal length. Now we're going to try to find some images, okay, to get a feel for what's going on. It's called ray diagrams. So what we're going to do it. When we have a formula or an equation, you will be able to do it the analytical method, which we will do, but the graphical method is also good to kind of get a feel of what's going on. Okay? So let's do the graphical method first. Yeah.
Why are you always making it so that it becomes a parallel line after the reflection? Or like one of the two sides of the reflection is always parallel?
Here?
Yeah.
I'm just trying to find the relationship between the focal point and the radius of curvature. For now, yeah. I'm going to now draw different rays. I'm going to draw another one. I'll draw 3 rays.
Okay.
And in fact, you can draw any number of rays. They should all go where the image is going to form. So let's see what. So let's start with this. Here is our concave mirror. Here is the focal point. Here is the center. This is F. This is the center. And I'm going to do 3 different possibilities. The first possibility is, let's say my object is here. The object is there. Yes. And then we're going to try to figure where the image is going to be. And we will send 3 rays. You can send 4 or 5, or just 2 rays are enough. Wherever 2 rays intersect, if they intersect, that's your image. Okay. So here is the first one. we're going to send a ray that is parallel to the axis. And what's the destiny of this?
Through the focal.
Through the focal point. Good. That's done. Now I'm going to send another ray. I'm going to send it through the focal point and then ask what happens to it. Here's another one. This one goes through the focal point, and the question is, what happens to it? Reflects in what direction? Reflects parallel. So these two rays intersect here. I'm going to draw a third one. A third possibility would be, because when you draw them, you should choose nice angles that you know what they are. Okay? In the case, I know what happens to parallel rays. I know what happens to rays that go through the focal point. I also know if I draw a ray that goes from here and then reflects there, I know what the angle is, because it's at the middle, so it's easy to figure that angle. So here's another ray. Didn't quite hit there, but you know what I mean. And then it will reflect, and approximately it will be here. So the tip of the arrow would be here. And you can do the middle and you can do the bottom, but we usually just do the tip, and then if the tip is there, I know the base would be, it's inverted. Okay, so that's the image. So let's think about this image. Does this image seem, first of all, is it real or virtual?
Real.
It is real, yeah, because it's the rays that met to make it, not their extensions. Is it upright or inverted? Inverted. Is S prime plus or minus? It's positive, because the object distance is on the same side as the reflected, as the outgoing rays. What's another thing that we mentioned before? I forget. Is it larger or smaller? What does it seem? It seems smaller, right? So it's a little smaller. So in that case, the magnification will have a value of a magnitude less than 1. Magnification, we will define it. It's the height of the object, the height of the image divided by the height of the object. Okay. Let's do 2 more. Next one, we drew one here. Next one, I'm going to draw one between C and F, and then ask what happens. So maybe our object will stand between C and F. The downside about drawing rays is just you have to be precise, right? Here is the object now. Let's say our object is here. We're going to draw the first ray, and it's going to go, let's try to make it parallel, and then it will reflect this way, right? Reflect that way. The next one, I'm going to draw it through the focal point, and then what happens to it? It will reflect parallel. You can see my parallel wasn't so parallel, it should be this way, right?